Tonight, we begin with a question that has quietly puzzled minds for centuries, one that emerges every time we taste the ocean's bitter embrace or feel the gentle touch of fresh rain on our skin. Why does the vast sea carry such a burden of salt, while the rain that falls from above arrives pure and clean? It's a mystery hidden in plain sight, woven into the very fabric of our planet's most fundamental processes. Take a moment to settle in. Perhaps adjust your position and let your breathing slow naturally. We're about to embark on a gentle journey through time and space, exploring the ancient dance between water, rock, and salt that has shaped our world for billions of years. This isn't a story of dramatic events or sudden changes, but rather the quiet, persistent work of nature, operating on scales so vast they dwarf human comprehension. The answer to our question lies not in any single moment, but in the accumulation of countless tiny processes, each one simple in itself, yet together creating the magnificent complexity of Earth's water systems. Tonight, we'll follow water on its eternal journey, from the depths of the ocean to the heights of the atmosphere, and back down to the land where it begins its slow transformation once again. Let your mind drift with me now, as we trace this ancient cycle that has been turning since the earliest days of our planet, long before life took hold, long before continents settled into their current forms. This is the story of how Earth became a world of salty seas and fresh rain, a tale written in the language of chemistry and time. Picture, if you will, the surface of a calm ocean on a warm, sunlit day. Gentle waves lap against an unseen shore, and above, wisps of water vapor rise invisibly into the air. This scene, peaceful and ordinary, contains within it the first key to understanding our question. For it is here, at the boundary between liquid and gas, that the great separation begins. Evaporation, the process that transforms liquid water into vapor, operates according to principles as old as matter itself. When energy from the sun strikes the ocean's surface, it provides individual water molecules with the kinetic force they need to break free from their liquid bonds. But this process is remarkably selective, and in that selectivity lies the first part of our answer. Water molecules, simple combinations of hydrogen and oxygen, require only modest amounts of energy to escape from the liquid state. They are held together by hydrogen bonds, relatively weak attractions that can be overcome by the gentle warmth of sunlight. But the ocean contains far more than just water molecules. Dissolved within its depths are countless ions, electrically charged particles that have arrived through processes we'll explore shortly. These ions, particularly sodium and chloride, which together form common salt, behave very differently from water molecules when energy is applied. They carry electrical charges that create much stronger attractions to the surrounding water molecules. These electrostatic forces are so powerful that under normal Earth conditions, salt ions simply cannot gain enough energy to evaporate. They remain behind, trapped in the liquid phase, while pure water molecules escape to join the atmosphere. This natural separation is so thorough, so complete, that it creates what is essentially a massive distillation process operating continuously across all the world's oceans. Every second of every day, pure water rises from salty seas, leaving behind every trace of dissolved material. The vapor that forms carries with it no memory of the salt it once mingled with, no residue of the minerals that gave the ocean its distinctive taste. As this pure water vapor rises through the atmosphere, it begins a transformation that will eventually return it to Earth as fresh precipitation. The atmosphere acts as a vast, invisible ocean where water molecules drift and dance, sometimes clustering around tiny particles of dust or pollen to form the nuclei of future raindrops. But even when these droplets grow and merge in the clouds above, they remain essentially pure, carrying at most trace amounts of atmospheric particles that pale in comparison to the salt content of seawater. When rain finally falls, it arrives as fresh water, sometimes so pure it's nearly indistinguishable from distilled water. This freshness isn't an accident or a gift from above. It's the inevitable result of evaporation's selective nature, a physical law as reliable as gravity itself. The rain that nourishes our crops, fills our rivers, and sustains all terrestrial life begins its journey in salty seas, but arrives at our doorstep, cleansed by the simple physics of phase change. Yet this raises an equally fascinating question. If rain is fresh, and rain ultimately comes from the ocean, how did the ocean become salty in the first place? The answer requires us to shift our focus from the sky to the land, from the rapid processes of evaporation to the almost imperceptibly slow work of geological time. Every raindrop that falls begins immediately to participate in one of Earth's most patient and persistent processes. As soon as fresh water touches the land, it begins to interact chemically with the rocks beneath. This interaction, gentle as a whisper, yet relentless as time itself, lies at the heart of how our planet's waters became divided into fresh and salt. Rainwater, despite its purity, is not chemically neutral. During its time in the atmosphere, it absorbs small amounts of carbon dioxide, forming weak carbonic acid. This slight acidity, barely perceptible to our senses, gives rainwater the ability to slowly dissolve certain minerals from the rocks it encounters. The process is so gradual that you could watch a rock for a human lifetime and see no change, yet over geological timescales, it reshapes entire continents. When this slightly acidic water seeps into cracks in rocks, or flows over exposed stone surfaces, it begins to break down the crystal structures that hold minerals together. Feldspar dissolves to release sodium and potassium. Limestone yields calcium and carbonate. Halite, where it exists, contributes chloride and more sodium. Each type of rock gives up its own distinctive combination of dissolved ions, creating a dilute solution that tastes nothing like seawater but contains the same basic ingredients. The quantities involved in this process are almost unimaginably small at any given moment. A single raindrop might dissolve only a few atoms of sodium from the grain of feldspar it contacts. A stream might carry away only parts per million of dissolved minerals. Yet, when these infinitesimal contributions are multiplied across every raindrop, every stream, every river on Earth, and then multiplied again across millions and millions of years, they add up to something extraordinary. Scientists estimate that the world's rivers collectively carry about 4 billion tons of dissolved salts to the oceans every single year. 4 billion tons sounds like an enormous number, and it is, but spread across the vastness of Earth's water cycle, it represents the accumulated effect of countless microscopic interactions between water and rock. Each molecule of dissolved sodium chloride in the sea began its journey as part of a crystal in some ancient rock, freed by the patient work of slightly acidic rainwater. This process of weathering and erosion has been operating continuously since Earth first had liquid water on its surface, perhaps 4 billion years ago. In the early days of our planet, when the oceans were young and the atmosphere was very different, the seas were likely much less salty than they are today. But year after year, century after century, millennium after millennium, the rivers kept flowing, each one carrying its invisible cargo of dissolved minerals downstream. The ocean, vast as it is, acts as the ultimate destination for all this dissolved material. Unlike rivers, which are constantly refreshed by new rainfall, the ocean is essentially a closed system when it comes to dissolved salts. Water can leave through evaporation, but as we've seen, only pure water escapes. The salts remain behind, gradually accumulating and concentrating as the eons pass. This accumulation process helps explain why different bodies of water have such different salt contents. Rivers and lakes, constantly refreshed by rainfall and fed by streams carrying only tiny concentrations of dissolved minerals, remain fresh. But enclosed bodies of water, like the Great Salt Lake in Utah or the Dead Sea in the Middle East, can become far saltier than the ocean because water can only leave them through evaporation. concentrating whatever salts have been carried in over time. Yet this raises another puzzle that has intrigued scientists for generations. If rivers have been carrying salts to the ocean for billions of years, why isn't the sea much saltier than it is? Why hasn't this continuous input resulted in oceans too salty to support life? The answer lies in understanding that the Earth is not just accumulating salt in its oceans, but also removing it through various geological and biological processes that operate on the same vast timescales. Some salt is removed when seawater becomes trapped in shallow basins that eventually dry up, leaving behind thick deposits of evaporate minerals that can be buried and removed from the ocean system for millions of years. Some is incorporated into the shells and skeletons of marine organisms, from microscopic plankton to massive coral reefs, effectively mining dissolved minerals from seawater and locking them away in biological structures. Deep beneath the ocean floor, seawater seeps into hot volcanic rocks, where high temperatures drive chemical reactions that can remove certain dissolved substances while adding others. These hydrothermal processes operate at scales and temperatures far removed from our everyday experience. Yet they play a crucial role in maintaining the chemical balance of seawater over geological time. The result of all these processes, operating simultaneously over billions of years, is a dynamic equilibrium. The ocean's saltiness has remained relatively stable for hundreds of millions of years, not because nothing is changing, but because inputs and outputs have come into balance. The 4 billion tons of salt carried to the sea each year by rivers is approximately balanced by various removal processes, keeping the ocean's salinity within a range that has allowed life to evolve and flourish. This balance is one of the most remarkable features of our planet's water system. It represents the operation of natural feedback mechanisms on a global scale, processes so large and slow that they dwarf human experience, yet so precise that they maintain conditions suitable for life. The saltiness of the sea is not random or arbitrary, but the product of countless interacting processes that have found their own equilibrium over deep time. Understanding this balance helps us appreciate the true answer to our original question. The sea is salty not because it started that way, but because it has spent billions of years accumulating the dissolved minerals weathered from all the Earth's rocks. Rain is not salty because evaporation is selective, taking only pure water and leaving dissolved substances behind. These two facts, simple in themselves, connect to reveal the operation of one of Earth's most fundamental cycles. As we drift deeper into this gentle exploration of our planet's waters, let yourself appreciate the quiet majesty of these processes. Every drop of rain that has ever fallen, every grain of salt that has ever dissolved, every molecule of water that has ever evaporated, has participated in this ancient dance. It is a dance without music that we can hear, without steps that we can see, yet it shapes our world more profoundly than any human activity. The water cycle that creates fresh rain from salty seas operates with a precision and reliability that has sustained our planet for eons. It asks nothing of us, requires no maintenance or oversight, yet provides the foundation for all terrestrial life. In its quiet operation, we can glimpse something of the deeper patterns that govern our universe, processes so fundamental that they seem almost like natural laws written into the very fabric of reality. Tonight, as you listen to these words, millions of water molecules are evaporating from ocean surfaces around the world, beginning their journey into the atmosphere. Somewhere else, rain is falling on ancient rocks, beginning the slow process of dissolution that will eventually carry new minerals to the sea. These processes connect every drop of water on Earth into one vast, interconnected system that has been operating since long before life began and will continue long after we are gone. In this vast interconnected system, we find ourselves witnessing something truly extraordinary. The water that falls as rain today may have been part of ancient seas millions of years ago, may have been locked in ice at the poles, may have flowed through countless rivers, may have nourished forests that no longer exist. Each molecule carries with it no memory of these journeys, yet collectively they participate in a story that spans the entire history of our planet. The selectivity of evaporation reveals itself as one of nature's most elegant solutions to a complex problem. How do you separate pure water from a solution containing dozens of different dissolved substances? The answer emerges from the fundamental properties of matter itself. Water molecules, with their simple structure and relatively weak intermolecular bonds, can escape to the gas phase with modest amounts of energy. But the ions that give seawater its saltiness are held in solution by much stronger forces. When sodium chloride dissolves in water, it doesn't simply float around as tiny particles. Instead, it breaks apart into sodium ions with positive electrical charges and chloride ions with negative charges. These charged particles attract water molecules much more strongly than water molecules attract each other. The result is that salt ions become surrounded by shells of water molecules, creating structures that require far more energy to break apart than pure water needs to evaporate. This difference in energy requirements creates a natural separation process that operates with remarkable efficiency. Under the gentle warmth of sunlight, water molecules can gain enough kinetic energy to break free from the ocean's surface and rise into the atmosphere. But the salt ions, held captive by their electrical attractions to surrounding water molecules, remain behind in the liquid phase. No amount of ordinary solar heating can provide enough energy to lift these charged particles into the atmosphere along with the water. The precision of this separation becomes even more remarkable when we consider the molecular scale at which it operates. Recent research has revealed that evaporation is not simply a matter of individual molecules randomly gaining enough energy to escape. Instead, it involves coordinated interactions between multiple water molecules, where one molecule gains its freedom through precise timing and energy transfer with its neighbours. At the exact moment of evaporation, a water molecule at the surface must interact with at least two other molecules in a carefully choreographed sequence. The energy transfer and bond breaking must occur in perfect synchronization, allowing one molecule to escape while the others remain in the liquid. This molecular dance happens billions of times every second across the world's oceans, yet it never captures the dissolved salts that remain permanently excluded from this escape process. As pure water vapor rises through the atmosphere, it enters a realm governed by different physical laws but following the same principles of molecular behavior. The atmosphere itself acts as a vast laboratory where water molecules undergo continuous phase transitions, clustering around microscopic particles to form the nuclei of future clouds. These condensation nuclei might include tiny grains of dust carried by wind, particles from volcanic eruptions, or even molecules released by living organisms, but they represent only the tiniest fraction of the mass of the resulting water droplets. Sometimes, these condensation nuclei include salt particles that have been carried into the atmosphere by wind blowing over ocean waves. When seawater spray evaporates in the air, it can leave behind microscopic salt crystals that drift on air currents and eventually serve as condensation points for water vapor. But even when raindrops form around these salt particles, the resulting precipitation contains salt concentrations thousands of times lower than seawater. The dilution effect is so powerful that rain formed around salt nuclei still qualifies as fresh water for all practical purposes. The journey from evaporation to precipitation typically takes about 10 days for any given water molecule, though this average conceals enormous variation. Some molecules condense quickly and fall as rain near their source, while others may travel thousands of miles and remain in the atmosphere for weeks before returning to Earth. During this atmospheric residence, water molecules may cycle repeatedly between vapor and liquid phases as they move through different temperature and pressure conditions in the constantly changing atmosphere. Throughout this entire atmospheric phase of the water cycle, the fundamental separation between water and salt remains absolute. No process in the atmosphere can reintroduce significant amounts of dissolved minerals into the pure water vapor that originated from the oceans. The rain that eventually falls carries only the faintest traces of atmospheric particles, maintaining the essential freshness that characterizes all precipitation on our planet. This atmospheric purification process operates on a scale so vast it challenges human comprehension. Every year, approximately 500,000 cubic kilometers of water evaporate from the Earth's surface, primarily from the oceans. This volume represents enough water to cover the entire continental United States to a depth of about 60 meters. All of this water rises into the atmosphere as pure vapor, leaving behind every trace of dissolved salt and other minerals. The same volume of pure water returns to Earth's surface as precipitation, though not necessarily in the same locations where it evaporated. The atmosphere acts as a global redistribution system, carrying moisture from the oceans to the continents and from tropical regions toward the poles. This redistribution is crucial for maintaining the freshwater resources that sustain all terrestrial life, from the smallest soil microorganisms to the largest mammals. When this fresh precipitation reaches the land, it immediately begins the next phase of the great cycle that connects rain to salt. The moment rainwater touches exposed rock or soil, chemical reactions begin that will eventually contribute new dissolved minerals to the sea. But these reactions proceed at rates so slow they seem almost motionless when measured against human timescales. The chemical weathering of rocks represents one of Earth's most patient processes. Even the hardest granite, given enough time and exposure to slightly acidic rainwater, will gradually surrender its constituent minerals to the flowing water. Feldspar crystals slowly release sodium, potassium, and aluminum. Mica contributes potassium and magnesium. Quartz, the most resistant common mineral, eventually yields trace amounts of silica to the persistent chemical assault of rainwater. Each of these weathering reactions follows well-established principles of chemistry, but they occur so slowly that their effects become apparent only when viewed across thousands or millions of years. A single raindrop might dissolve only a few thousand atoms from the rock surface it contacts. But when this process is multiplied across every raindrop that falls, every rock surface that exists, and every moment of geological time, the cumulative effect becomes enormous. The rate of weathering depends on many factors that vary across Earth's surface. Temperature plays a crucial role because chemical reactions proceed faster in warmer conditions. This is why tropical regions contribute disproportionately large amounts of dissolved minerals to the world's rivers compared to polar areas. Rainfall intensity and frequency also matter because more water means more chemical weathering, but the relationship is complex because steady, gentle rain often causes more total weathering than brief, intense storms. The type of rock being weathered makes an enormous difference in both the rate of dissolution and the types of minerals released. Limestone and other carbonate rocks dissolve relatively quickly in acidic water, contributing calcium and carbonate ions to streams and rivers. Basalt and other volcanic rocks weather more slowly, but release different combinations of minerals, including significant amounts of magnesium and iron. Sandstone contributes mainly silica, while shale adds various clay minerals and trace elements to the weathering mix. Even the biological activity in soil affects weathering rates. Plant roots produce acids that can accelerate the breakdown of minerals, while soil bacteria and fungi contribute their own chemical compounds that participate in weathering reactions. The organic acids produced by decomposing plant matter can be much stronger than the carbonic acid formed when carbon dioxide dissolves in rainwater, creating localized environments where weathering proceeds much faster than it would in sterile conditions. As water moves from the soil into streams and then into larger rivers, it carries with it the dissolved products of all these weathering reactions. The concentration of dissolved minerals in river water is typically very low, often measured in parts per million. but the total volume of water involved makes the annual contribution significant. The Amazon River alone carries approximately 100 million tons of dissolved minerals to the Atlantic Ocean each year, while the Mississippi River contributes about 40 million tons to the Gulf of Mexico. These numbers, impressive as they sound, represent only a tiny fraction of the total dissolved mineral content of the world's rivers. Hundreds of major rivers and thousands of smaller waterways all contribute their share of weathered rock to the sea. When all these contributions are summed globally, they amount to the 4 billion tons of dissolved salts that reach the oceans annually, a number that represents the cumulative effect of rock weathering across the entire planet. The journey from rock to river to ocean can take vastly different amounts of time depending on geographic and geological circumstances. Water that falls on a steep mountain slope might reach the sea within days or weeks, carrying with it only the minerals it could dissolve during its brief contact with rock surfaces. But water that soaks into deep groundwater systems might spend thousands of years underground, slowly percolating through rock formations and accumulating much higher concentrations of dissolved minerals before finally emerging in springs that feed into surface water systems. These groundwater contributions often carry distinctive chemical signatures that reflect the specific rock formations they have contacted during their long underground journeys. Water emerging from limestone aquifers tends to be rich in calcium and carbonate ions. Groundwater from sandstone formations carries more silica. Water that has contacted salt deposits deep underground can emerge with mineral concentrations approaching those of seawater, though such highly mineralized groundwater represents only a small fraction of the total freshwater flow to the oceans. The chemical composition of river water varies not only between different rivers, but also seasonally within the same river system. During periods of high rainfall and rapid runoff, rivers typically carry lower concentrations of dissolved minerals because the water has had less time to interact with rock surfaces. During dry periods when flow is sustained primarily by groundwater, mineral concentrations often increase because groundwater has typically had much longer contact time with rock formations. These seasonal variations in river chemistry reflect the complex interplay between climate, geology, and hydrology that governs the rate at which minerals are transferred from land to sea. Understanding these variations helps scientists track how changes in precipitation patterns might affect the global salt balance of the oceans, though such changes occur so slowly that their effects become apparent only when measured over decades or centuries. The ultimate destination for all this dissolved mineral matter is the world's oceans, where it joins the vast inventory of salts that have been accumulating for billions of years. But the ocean is not simply a passive reservoir that grows saltier with each passing year. Instead, it represents a dynamic system where salt inputs are balanced by various removal processes, creating a complex equilibrium that has maintained relatively stable salinity levels for hundreds of millions of years. The removal of salt from seawater occurs through several different mechanisms, each operating on its own characteristic timescale. Some processes remove salt relatively quickly, while others work over geological time periods that span millions of years. Together, these removal mechanisms balance the continuous input from weathering and river transport, preventing the oceans from becoming impossibly salty. One of the most important salt removal processes involves the formation of evaporate deposits in shallow, restricted marine basins. When seawater becomes trapped in areas where evaporation exceeds the inflow of fresh seawater, the dissolved minerals become concentrated until they begin to precipitate out of solution as crystalline deposits. These evaporate formations can accumulate to enormous thicknesses over geological time, effectively removing vast quantities of salt from the ocean system. Modern examples of evaporate formation can be observed in places like the Dead Sea, where the combination of high evaporation rates and limited water exchange with the open ocean has created mineral concentrations several times higher than normal seawater. As water continues to evaporate from such systems, different minerals precipitate in sequence, with the most abundant salts forming thick layers that can be buried and preserved in the geological record for millions of years. Millions of years. Biological processes in the ocean represent another major pathway for salt removal from seawater. Marine organisms, from the smallest plankton to the largest coral reefs, actively extract dissolved minerals to build their shells, skeletons, and other hard structures. This biological mining of seawater operates continuously in every drop of ocean water, creating a vast living system that selectively removes specific ions while leaving others in solution. Microscopic organisms called foraminifera construct intricate shells from calcium carbonate, each one no larger than a grain of sand, yet requiring thousands of calcium and carbonate ions extracted from the surrounding seawater. When these tiny creatures die, their shells drift slowly to the ocean floor, carrying their cargo of crystallized minerals away from the water column. Over millions of years, these microscopic shells accumulate into limestone deposits hundreds of meters thick, representing enormous quantities of minerals permanently removed from the sea. Larger marine organisms participate in this same process on different scales. Mollusks like oysters and clams filter vast volumes of seawater through their bodies, extracting calcium to build their protective shells. A single oyster might filter 50 gallons of seawater each day, removing tiny amounts of dissolved calcium with each cycle. Multiplied across the billions of shell-building creatures in the world's oceans, this biological extraction becomes a significant factor in the global salt balance. Coral reefs demonstrate this biological salt removal on the grandest scale. These living cities beneath the waves consist almost entirely of calcium carbonate structures built by countless generations of tiny coral animals. The Great Barrier Reef alone contains enough crystallized calcium carbonate to rival some of the world's largest limestone mountain ranges. Every grain of this vast structure began as dissolved minerals in seawater, extracted by living organisms and transformed into solid rock through biological processes. Even microscopic plants participate in modifying seawater chemistry. Diatoms, single-celled algae that drift in vast numbers through the upper layers of the ocean, construct elaborate glass houses from dissolved silica. These microscopic architects extract silicon compounds from seawater to build their intricate shells, which display geometric patterns of stunning complexity. When diatoms die, their silica shells sink to the ocean floor, gradually accumulating into deposits that can extend for thousands of square kilometers. The collective effect of all these biological processes is to continuously mine the ocean for specific dissolved substances. Unlike the input of minerals from rivers, which add salt to the sea, biological extraction removes salt from solution and concentrates it in solid structures. This biological pump operates with remarkable efficiency, processing the entire volume of the world's oceans multiple times over geological periods. Deep beneath the ocean floor, another set of processes works to modify seawater chemistry through direct interaction with hot volcanic rocks. Where tectonic plates spread apart along mid-ocean ridges, seawater seeps down through cracks in the newly formed sea floor, penetrating several kilometers into the hot rock below. The temperatures in these deep circulation systems can exceed 400 degrees Celsius, hot enough to drive chemical reactions that dramatically alter both the water and the rock. As seawater descends through this underground plumbing system, the extreme heat and pressure cause it to lose some dissolved substances while gaining others. Magnesium and sulfate ions, abundant in normal seawater, react with the hot rock and are removed from solution. Meanwhile, the water strips metals like iron, copper, and zinc from the surrounding volcanic minerals, creating a chemically transformed fluid that bears little resemblance to ordinary seawater. When this altered water eventually finds its way back to the surface through hydrothermal vents, it carries with it the chemical signature of its underground journey. The black smoke vents that dot the mid-ocean ridges represent the visible manifestation of this hidden circulation system, spewing forth water that has been chemically transformed by its passage through the hot depths of the seafloor. This hydrothermal circulation represents one of the most important mechanisms for removing certain dissolved substances from seawater while adding others. The scale of this process is enormous, with the entire volume of the world's oceans cycling through these underground systems approximately every 10 million years. Over geological time, this circulation has profoundly influenced the chemical composition of seawater, helping to maintain the balance between inputs and outputs that keeps ocean salinity stable. The formation of new minerals on the seafloor provides yet another pathway for salt removal from the oceans. When seawater comes into contact with fresh volcanic rock, chemical reactions often produce entirely new mineral compounds that incorporate dissolved ions from the water. These orthogenic minerals, as they are called, grow directly from seawater and represent a form of chemical precipitation that permanently removes dissolved substances from solution. Clay minerals form when dissolved aluminum, silicon, and other elements combine in the presence of seawater to create new crystalline structures. These clays slowly accumulate on the ocean floor, building layers that can eventually become thick sedimentary deposits. Iron and manganese oxides precipitate from seawater under certain conditions, forming nodules and crusts that carpet vast areas of the deep sea floor. Each of these mineral formation processes removes specific dissolved substances from seawater, contributing to the overall chemical balance of the oceans. The interaction between seawater and sediments on the ocean floor creates another complex system of chemical exchange. As organic matter from dead plankton and other marine organisms settles to the bottom and begins to decompose, it creates chemical environments that can either add substances to or remove substances from the overlying water. Some sediments act as chemical sponges, absorbing dissolved substances from seawater and locking them away in the sediment column. Others release previously buried chemicals back into the water, adding to the dissolved load of the overlying sea. These sediment-water interactions operate over vast areas of the ocean floor and can significantly influence local water chemistry. In some regions, the chemical exchange between sediments and seawater represents the dominant factor controlling the concentration of certain dissolved substances. The cumulative effect of these interactions across all the world's ocean basins contributes to the global balance that maintains stable seawater composition over geological time. The burial of salt in deep sedimentary basins provides another long-term removal mechanism that operates over millions of years. When thick sequences of sediments accumulate in areas like river deltas or deep ocean trenches, they can trap seawater in the pore spaces between sediment grains. As these sediments are buried deeper and deeper by additional layers, the trapped seawater becomes isolated from the overlying ocean, and its dissolved salts are effectively removed from the active ocean system. This process of salt burial operates slowly but steadily across all the world's sedimentary basins. The sediments that accumulate in these areas contain varying amounts of trapped seawater, and as burial continues over millions of years, this represents a significant pathway for removing salt from the ocean system. Some of this buried salt may eventually return to the surface through tectonic processes that uplift and expose ancient sedimentary rocks, but the timescales involved are so long that the burial process effectively removes salt from the active ocean system for geological ages. The balance between all these salt removal processes and the continuous input from rivers creates a dynamic equilibrium that has maintained ocean salinity within a relatively narrow range for hundreds of millions of years. This balance is not static, but responds to changes in global climate, tectonic activity, and biological productivity. During ice ages, for example, the storage of fresh water in continental ice sheets can temporarily increase ocean salinity. During periods of intense volcanic activity, increased hydrothermal circulation might accelerate certain salt removal processes. Despite these fluctuations, the fundamental balance between salt inputs and outputs has remained remarkably stable over the time scales relevant to the evolution of life. This stability suggests that Earth's ocean atmosphere system contains powerful feedback mechanisms that resist large changes in seawater composition. When salt inputs increase, removal processes tend to accelerate. When inputs decrease, removal processes slow down correspondingly. Understanding this balance helps explain why the ocean has maintained conditions suitable for life over billions of years of Earth history. The salinity of seawater affects virtually every aspect of marine ecosystems, from the basic physiology of individual organisms to the large-scale circulation patterns that distribute heat and nutrients throughout the world's oceans. The stability of this chemical environment has provided a foundation upon which the incredible diversity of marine life could evolve and flourish. The timescales involved in these processes dwarf human experience and challenge our ability to comprehend change that occurs over millions of years. Yet these slow, patient processes have shaped our planet more profoundly than any catastrophic event. The salt content of the sea, the freshness of rain, the composition of river water, all reflect the operation of these ancient cycles that connect every drop of water on Earth into one vast interconnected system. As we follow this gentle exploration deeper into the mechanisms that govern our planet's waters, let yourself appreciate the elegant simplicity underlying such complexity. The same physical and chemical laws that govern the behavior of a single water molecule also control the composition of entire oceans. The same processes that weather a single grain of feldspar also shape the chemistry of rivers that drain entire continents. In the quiet operation of these natural cycles, we glimpse something of the profound order that underlies our universe. Water evaporates and condenses according to physical laws that operate with perfect consistency across all of space and time. Minerals dissolve and precipitate following chemical principles that remain constant from the smallest laboratory sample to the largest geological formation. The cycles that separate salt from fresh water operate without conscious intent, yet they create and maintain the conditions that make life possible. Tonight, as you rest and let these thoughts settle into your consciousness, remember that you are witnessing processes that connect you to the deepest history of our planet. The water in your body has likely traveled through these cycles countless times, perhaps falling as rain on ancient continents, flowing through rivers that no longer exist, spending eons dissolved in seas that have long since dried up. Each molecule carries no memory of these journeys, yet collectively they participate in the grand circulation that has sustained our world since the earliest days of liquid water on Earth. The boundary between fresh and salt water that seems so absolute to our senses reveals itself as part of a continuous cycle of transformation. Rain becomes rivers, becomes seas, become clouds, become rain again. Each phase transition governed by the same fundamental forces, each transformation maintaining the essential separation between pure water and dissolved minerals. In this endless circulation, we find not just the answer to our question about why seas are salty, but rain is not, but a window into the elegant mechanisms that sustain our living planet. The dance between water and minerals plays out not just in the obvious places like rushing rivers and crashing waves, but in the hidden spaces beneath our feet, where groundwater moves with the patience of centuries through layers of rock and soil. These underground rivers, invisible to our eyes, carry out the same slow dissolution process that surface waters perform, but with even more time to work their chemical magic on the surrounding stone. Deep beneath the surface, water that fell as rain, decades or even centuries ago, continues its journey through networks of tiny cracks and porous spaces in the rock. Down here, in the eternal darkness, time moves differently. A single drop of water might spend 1,000 years slowly percolating through limestone, gradually dissolving microscopic amounts of calcium with each passing decade. The concentration of minerals that accumulates in this groundwater can become quite high, far higher than in the surface streams that rush quickly over rocks, with barely enough time to dissolve more than traces of minerals. When this ancient groundwater finally emerges from springs, it brings with it the accumulated chemical signature of its long underground journey. Springs that flow from limestone aquifers taste distinctly different from those that emerge from granite formations, each one carrying the specific mineral fingerprint of the rocks through which it has travelled. These underground contributions to the global mineral transport system represent some of the most concentrated sources of dissolved substances that eventually reach the sea. The temperature deep underground also affects these chemical processes in ways that surface weathering cannot replicate. In the deeper parts of the Earth's crust, where groundwater encounters rocks heated by the planet's internal warmth, chemical reactions proceed more rapidly, despite the absence of sunlight. Hot springs and geothermal features provide dramatic examples of this underground chemistry, often carrying mineral concentrations that approach those of seawater itself, though from entirely different sources. Even in these extreme underground environments, the fundamental selectivity of evaporation continues to operate according to the same physical laws. When geothermal waters reach the surface and begin to evaporate in hot springs or geysers, pure water vapor still rises while dissolved minerals remain behind, often precipitating into colourful deposits of travertine, silica, or other crystalline formations. These geological sculptures, built grain by grain from minerals that once flowed in solution, demonstrate the same separation process that operates globally between the ocean and the atmosphere. The volcanic processes that shape our planet also contribute their own distinctive chemistry to the global circulation of minerals. When molten rock cools and solidifies, either on the surface as lava flows or deep underground as intrusive formations, it creates fresh mineral surfaces that are particularly susceptible to chemical weathering. Volcanic rocks often contain minerals that dissolve more readily than the ancient weathered rocks found in stable continental areas, contributing disproportionately large amounts of dissolved substances to nearby streams and rivers. Volcanic eruptions themselves add materials directly to both the atmosphere and the oceans. Volcanic gases contain sulfur compounds that dissolve in rainwater, making it even more acidic and increasing its ability to weather rocks. Volcanic ash, spread across vast areas by wind, provides fresh mineral surfaces that weather rapidly when exposed to rain. The minerals released by these weathering processes often differ from those produced by the weathering of older rocks, adding their own unique chemical signatures to the global mix of dissolved substances flowing toward the sea. The islands of the Pacific Ocean provide natural laboratories for studying how volcanic materials contribute to ocean chemistry. These islands, built entirely from volcanic rocks erupted from the seafloor, experience some of the most rapid weathering rates on Earth. The combination of warm, humid climates and fresh volcanic minerals creates conditions where rocks dissolve much faster than on older continental surfaces. The streams flowing from these volcanic islands carry unusually high concentrations of dissolved minerals, despite their relatively short flow paths from mountain peaks to the sea. Even the biological processes that seem separate from the physical chemistry of weathering play crucial roles in determining how minerals move from rocks to rivers to oceans. Plant roots don't simply anchor themselves in soil, they actively modify the chemical environment around them by releasing organic acids that can dissolve minerals much more effectively than pure rainwater. The carbon dioxide produced by soil organisms and plant roots dissolves in the soil water to create concentrations of carbonic acid far higher than those found in ordinary rainwater. Forests, with their deep root systems and abundant organic matter, create particularly aggressive chemical environments for rock weathering. The soil beneath a mature forest might contain organic acids strong enough to dissolve minerals that would remain stable for centuries in bare rock. The Amazon rainforest, despite growing on some of the most nutrient-poor soils on Earth, maintains its incredible biological productivity, partly by creating chemical conditions that maximize the extraction of minerals from the underlying bedrock. The seasonal cycles that govern plant growth and decay also create rhythmic variations in weathering intensity. During growing seasons, when plants are actively producing organic acids and root systems are expanding, weathering rates increase. During dormant periods, when biological activity slows, the chemical attack on minerals decreases correspondingly. These biological rhythms add another layer of complexity to the already intricate processes that move minerals from land to sea. Microorganisms, though invisible to the naked eye, represent some of the most important agents of chemical weathering on our planet. Bacteria and fungi produce acids and other chemical compounds that can break down even the most resistant minerals. Some microorganisms actually derive energy from chemical reactions involving rock minerals, creating biological mining operations that operate on microscopic scales but collectively process enormous quantities of material. These biological weathering processes often concentrate their effects along the boundaries between different types of rock or at the interfaces between rock and soil. The result is that weathering doesn't proceed uniformly across all rock surfaces, but instead follows complex patterns determined by the intersection of geology, climate, topography, and biology. Understanding these patterns helps explain why some rivers carry much higher concentrations of dissolved minerals than others, even when flowing through apparently similar terrain. The ice ages that have periodically reshaped our planet's surface also profoundly influence the global circulation of minerals from land to sea. During glacial periods, massive ice sheets scraped across continental surfaces, grinding fresh rock to powder and creating enormous quantities of finely divided mineral matter. When these ice sheets melted, they released floods of water carrying suspended sediments and dissolved minerals in concentrations far higher than normal rivers. The landscapes left behind by retreating glaciers provided particularly fertile ground for rapid chemical weathering. Glacial erosion exposes fresh rock surfaces that have never been weathered, creating conditions where chemical reactions can proceed much more rapidly than on older, weathered surfaces. The powdered rock left behind by glacial grinding provides enormous surface areas for chemical attack by rainwater, accelerating the dissolution process far beyond normal rates. Even today, regions that were glaciated during the most recent ice age continue to experience higher than normal weathering rates as a consequence of their geological youth. The Great Lakes region of North America, the Scandinavian Peninsula, and large areas of Canada all show evidence of this enhanced weathering in the chemistry of their rivers and lakes. These areas contribute disproportionately large amounts of dissolved minerals to the global ocean system, despite their relatively cold climates that would normally slow chemical processes. The timing of glacial cycles also created periods of dramatically lowered sea levels, when vast quantities of water were locked up in continental ice sheets. During these periods, the concentration of salt in the reduced volume of seawater increased, creating chemical conditions quite different from those that exist today. When the ice sheets melted and sea levels rose again, the returning fresh water diluted the ocean back toward its normal salinity, but the process took thousands of years to reach equilibrium. These glacial influences on ocean chemistry demonstrate that the balance between fresh and salt water on our planet is not static, but responds to large-scale climate changes over geological time. The stability of ocean salinity that characterizes the current interglacial period represents just one state in a complex system that has experienced significant variations throughout Earth's history, yet has always returned to conditions that support life. The movement of continents themselves, driven by the slow but inexorable forces of plate tectonics, creates another dimension of change in the global circulation of minerals. As continents drift across the Earth's surface over millions of years, they encounter different climate zones that dramatically affect weathering rates. Continents that move from polar to tropical latitudes experience accelerated chemical weathering as they enter warmer, wetter climates. Conversely, land masses that drift into arid regions see their contribution of dissolved minerals to the oceans decrease as weathering slows in the absence of adequate rainfall. The collision of continents creates mountain ranges that expose fresh rock to weathering, while also affecting regional and global climate patterns. The uplift of the Himalayas, for example, not only provided enormous quantities of fresh rock for weathering, but also altered atmospheric circulation patterns across much of Asia, affecting rainfall distribution and temperature patterns that influence weathering rates across a vast region. The erosion of these young mountains contributes some of the highest mineral loads of any river system on Earth to the Indian Ocean. The breakup of continents creates new ocean basins and changes the patterns of water circulation that affect how dissolved minerals are distributed and concentrated in different parts of the sea. When the Atlantic Ocean first began to open as the supercontinent Pangaea split apart, it created new pathways for water circulation and new patterns of evaporation and precipitation that influenced the global distribution of salinity. These tectonic processes operate over timescales of hundreds of millions of years, yet their effects on water chemistry can be traced in the geological record preserved in ocean sediments. The chemical composition of ancient seawater, preserved in the mineral deposits and fossils found in rocks that formed on the seafloor millions of years ago, reveals that ocean chemistry has indeed changed significantly over geological time. These changes reflect not only variations in the rate of mineral input from weathering, but also changes in the biological and geological processes that remove minerals from seawater. The evolution of shell-building organisms, for example, dramatically increased the rate at which calcium carbonate was removed from the oceans, affecting the chemical balance of seawater in ways that can still be measured today. The sulfur content of ancient seawater appears to have varied significantly over geological time, reflecting changes in volcanic activity and the evolution of sulfur metabolizing bacteria. The concentration of silica in seawater has decreased over the past several 100 million years as diatoms and other silica-secreting organisms evolved and began extracting this dissolved substance from the oceans. These biological innovations represent evolutionary events that permanently altered ocean chemistry by creating new pathways for removing dissolved materials from seawater. Even the oxygen content of Earth's atmosphere has influenced ocean chemistry over geological time. During periods when atmospheric oxygen levels were lower than today, different chemical reactions dominated the weathering process, leading to different suites of dissolved minerals being transported to the oceans. The rise of oxygen-producing photosynthesis fundamentally altered the chemistry of both the atmosphere and the oceans, creating oxidizing conditions that changed the solubility and transport behavior of many elements. These deep time perspectives on ocean chemistry help explain why the current balance between salt inputs and outputs represents just one state in a dynamic system that has experienced enormous changes over the history of our planet. Yet through all these changes, the fundamental physics of evaporation has remained constant, continuing to separate pure water from dissolved substances with the same selectivity that operates today. This physical constancy has provided a stable foundation for the water cycle, even as the chemical details of that cycle have evolved. The role of life itself in modifying the movement of minerals from land to sea extends far beyond the direct effects of weathering by plant roots and soil organisms. The evolution of land plants fundamentally changed weathering rates by creating soils rich in organic matter and by dramatically altering the hydrological cycle through transpiration. Before land plants evolved, weathering proceeded much more slowly because there were no biological mechanisms for concentrating organic acids in the surface layers where rock meets water. The colonization of land by plants and animals also created entirely new pathways for moving minerals around the landscape. Plants extract minerals from deep in the soil through their root systems and concentrate them in leaves and wood that eventually decompose on the surface, creating localized areas of enhanced mineral availability. Animals transport minerals over long distances through their movements and waste products, creating patterns of mineral distribution that would not exist in a purely physical system. Human activities have begun to modify these ancient cycles in ways that are only beginning to be understood. agriculture concentrates certain minerals in some areas while depleting them in others, changing local patterns of weathering and mineral transport. Mining operations expose fresh rock surfaces to weathering while also directly transferring large quantities of minerals from deep underground to the surface environment. Industrial activities add entirely new chemical compounds to the weathering system, some of which have no natural analogues in the geological record. The burning of fossil fuels has increased the carbon dioxide content of the atmosphere, making rainwater more acidic and potentially increasing weathering rates globally. This enhanced weathering might seem beneficial as a way of removing excess carbon dioxide from the atmosphere, but it also accelerates the transport of other dissolved substances to the oceans in ways that could affect marine ecosystems. The full consequences of these human modifications to the global mineral cycle are still being studied and understood. Climate change driven by human activities also threatens to alter the delicate balance between evaporation and precipitation that maintains the separation between fresh and salt water. Changes in temperature and precipitation patterns could shift the locations where weathering occurs most rapidly, alter the seasonal timing of mineral transport by rivers, and modify the evaporation rates that drive the global water cycle. These changes operate on timescales much faster than the geological processes that establish the current balance, potentially creating rapid shifts in conditions that have remained stable for millions of years. Yet even in the face of these rapid changes, the fundamental physical and chemical processes that govern the behavior of water and dissolved minerals continue to operate according to the same natural laws that have shaped our planet for billions of years. Water molecules still evaporate selectively, leaving dissolved substances behind. Rainwater still weathers rocks at rates determined by temperature, acidity, and mineral composition. Rivers still carry their dissolved cargo toward the sea, where biological and geological processes still work to remove excess salts from the ocean system. The resilience of these natural cycles, their ability to maintain function even under changing conditions, reflects the deep stability of the physical laws that govern matter and energy. The same quantum mechanical principles that determine how electrons are shared between atoms in chemical bonds also control the large-scale processes that separate continents and oceans. The same thermodynamic laws that govern the evaporation of a single water molecule also drive the circulation patterns that distribute heat and moisture around the entire planet. In contemplating these connections between the smallest and largest scales of natural processes, we begin to appreciate the profound unity that underlies the apparent complexity of Earth's systems. The saltiness of the sea and the freshness of rain are not separate phenomena, but different aspects of a single integrated system that operates according to consistent physical principles across all scales of space and time. As we near the end of this gentle exploration of our planet's waters, let yourself rest in the knowledge that these ancient cycles continue their patient work, regardless of human awareness or intervention. Right now, as you listen to these words, water is evaporating from ocean surfaces around the world, beginning its atmospheric journey as pure vapor. Somewhere else, rain is falling on exposed rocks, starting the slow chemical process that will eventually carry new minerals to the sea. These processes ask nothing of us, require no conscious oversight, yet they maintain the conditions that make all life possible. The water cycle that creates our distinction between fresh and salt water operates with a reliability and precision that has sustained our planet for eons. It represents one of the most elegant solutions in nature, using the simple physics of phase change to maintain chemical conditions suitable for life. In its quiet operation, we glimpse something of the deeper order that governs our universe, patterns so fundamental that they seem woven into the very fabric of reality. Tonight, as you drift towards sleep, remember that you are witnessing processes that connect every drop of water on Earth into one vast, interconnected system. The rain that will fall tomorrow may contain molecules that once flowed in ancient rivers, that spent millennia dissolved in long-vanished seas, that rose as vapor from oceans that existed before complex life evolved on our planet. Each molecule carries no memory of these journeys, yet collectively, they participate in cycles that have operated since the earliest days of liquid water on Earth. The boundary between fresh and salt water that seems so absolute reveals itself as part of a continuous circulation of transformation and renewal. Water changes phase from liquid to gas to liquid again, but it never loses its essential character. Salt dissolves and precipitates, moves from rock to river to sea to sediment, but it too follows predictable patterns governed by physical law. In this endless circulation, matter neither appears nor disappears, but simply changes form, participating in cycles that connect the smallest chemical reactions to the grandest geological processes. The mystery we began with tonight, why the sea is salty but rain is not, opens into a vast landscape of interconnected processes that have shaped our world since its beginning. In understanding these processes, we don't diminish their wonder, but rather discover that reality itself is far more intricate and beautiful than any simple explanation could suggest. The truth, when we finally glimpse it, reveals mechanisms so elegant and integrated that they inspire a deeper appreciation for the natural world that surrounds and sustains us. As you rest now, carried by the rhythm of these ancient cycles, let yourself feel connected to the deep processes that maintain our living planet. You are made largely of water that has participated in these cycles countless times, water that has fallen as rain and flowed in rivers and risen as vapor from distant seas. In your very substance, you carry the memory of these journeys, even as your consciousness prepares to drift into the restorative darkness of sleep. The gentle separation of salt from fresh water continues its patient work through the night, maintaining the chemical conditions that allow life to flourish in a universe that might otherwise be hostile to such delicate arrangements. In the morning, the sun will rise again to power another day of evaporation, another cycle of the great circulation that keeps our world balanced between the extremes of pure water and saturated brine. And in that daily renewal, we find both the answer to our question and a deeper appreciation for the quiet miracles that surround us always, hidden in plain sight, asking only that we pause long enough to notice their gentle presence in our lives. The story of how minerals move through our planet's systems reveals patterns that operate beneath our awareness, quietly shaping the very foundations of the world we inhabit. These processes unfold with such patience that they seem almost motionless, yet their cumulative effects have created the chemical landscape that defines our living planet. In the vast expanses of the deep ocean, far from any continental shore, volcanic activity continues to reshape the seafloor in ways that profoundly influence the chemistry of seawater. Along the mid-ocean ridges, where new oceanic crust is born from molten rock, seawater penetrates deep into the hot volcanic formations through networks of cracks and fissures. This descent into the Earth's interior subjects the water to temperatures and pressures that transform it completely. As seawater circulates through these hot rock systems, it undergoes chemical changes that would be impossible at the surface. The extreme conditions deep beneath the seafloor drive reactions between water and rock that strip away some dissolved substances while adding others. Magnesium and sulfate, abundant in normal seawater, react with the hot volcanic minerals and disappear from solution. Meanwhile, the superheated water dissolves metals like iron, copper, and zinc from the surrounding rock, creating fluids unlike anything found elsewhere on Earth. When this chemically altered water eventually returns to the seafloor through hydrothermal vents, it carries with it the signature of its underground journey. These vents, scattered along the mid-ocean ridges like underwater chimneys, represent the visible endpoints of circulation systems that process enormous volumes of seawater over geological time. The total flow through these systems is so vast that the entire volume of the world's oceans passes through this underground circulation approximately every 10 million years. This deep circulation represents one of the most important mechanisms for maintaining the chemical balance of seawater. Without these processes removing excess magnesium and sulfate, while adding other elements, the composition of seawater would be very different from what we observe today. The hydrothermal systems act as massive chemical processing plants, operating continuously in the hidden depths of the ocean to maintain conditions suitable for life. The black smoke events that mark these hydrothermal fields create their own unique ecosystems, sustained entirely by the chemical energy released when the hot, mineral-rich fluids mix with cold seawater. These communities of life exist in perpetual darkness, deriving their energy not from sunlight but from the chemical reactions that occur when two very different types of water meet and mingle. The organisms that thrive around these vents represent some of the most ancient forms of life on Earth, perhaps similar to the very first living systems that evolved in our planet's early oceans. The minerals precipitated when hot hydrothermal fluids encounter cold seawater create spectacular formations on the seafloor. Chimneys of sulfide minerals can grow to heights of several stories, built grain by grain, as dissolved metals crystallize from solution. These structures, though they may seem permanent, are actually quite ephemeral on geological timescales. As the underlying volcanic activity shifts, old vents become inactive and new ones form elsewhere, creating a constantly changing landscape of mineral formation and dissolution. The sediments that accumulate around these hydrothermal areas carry the chemical signature of these processes far from their source. Fine particles of metal-rich minerals settle across vast areas of the deep sea floor, gradually burying the evidence of past hydrothermal activity, while creating deposits that may eventually be uplifted and exposed on land through tectonic processes. These ancient hydrothermal deposits, now preserved in rocks on the continents, provide windows into the operation of these deep-sea processes throughout Earth's history. The role of atmospheric chemistry in the global water cycle extends far beyond the simple evaporation of pure water from the ocean surface. The atmosphere itself participates actively in chemical processes that affect the composition of precipitation and the rate at which rocks weather on the land surface. Carbon dioxide dissolved in atmospheric moisture creates the weak carbonic acid that gives rainwater its ability to weather rocks. But this is just one of many atmospheric contributions to the global chemical cycle. Volcanic eruptions inject sulfur compounds and other reactive gases into the atmosphere, where they dissolve in water droplets and affect the acidity of precipitation over vast regions. Major volcanic events can increase the acidity of rainfall globally for months or years, accelerating weathering processes and increasing the rate at which dissolved minerals are transported from land to sea. These volcanic contributions to atmospheric chemistry operate on much shorter timescales than the geological processes we've been exploring, yet they can have significant effects on the global chemical balance. Even the biological activity of marine organisms contributes gases to the atmosphere that influence precipitation chemistry. Phytoplankton in the surface, waters of the ocean release sulfur compounds that can serve as condensation nuclei for cloud formation, affecting both the location and the chemical composition of rainfall. These biological contributions to atmospheric chemistry create complex feedback loops between the ocean, atmosphere, and land surface that help regulate the global climate system. The seasonal cycles that govern biological activity also create rhythmic variations in atmospheric chemistry that affect precipitation patterns. During periods of high biological productivity in the oceans, the release of biogenic gases can influence cloud formation and precipitation chemistry over large regions. These biological rhythms add another layer of complexity to the already intricate processes that govern the movement of water and dissolved substances around our planet. The interaction between dust particles and atmospheric moisture creates another pathway for minerals to move between the land, atmosphere, and ocean systems. Wind erosion lifts fine particles from continental surfaces high into the atmosphere, where they can travel thousands of miles before settling back to Earth. When these dust particles encounter water vapor in the atmosphere, they can serve as condensation nuclei for cloud formation, potentially affecting the chemistry of the resulting precipitation. Some of this atmospheric dust eventually settles in the ocean, where it provides a direct input of terrestrial minerals to marine systems. The dust that blows from the Sahara Desert across the Atlantic Ocean, for example, carries nutrients that support biological productivity in distant parts of the ocean basin. This atmospheric transport of minerals represents a pathway for chemical exchange that operates independently of the river systems that dominate the transport of dissolved substances from land to sea. The chemical weathering of rocks on the continents operates according to principles that remain constant across all climates and geological settings, yet the rate and character of these processes vary dramatically depending on local conditions. Temperature plays a fundamental role because chemical reactions proceed faster at higher temperatures, but the relationship between temperature and weathering rate is complicated by the availability of water and the specific minerals being weathered. In tropical regions, where temperatures remain high throughout the year and rainfall is abundant, chemical weathering can proceed at rates that would be impossible in cooler or drier climates. The deep soils that develop in these regions reflect the intense chemical processing that occurs when rocks are exposed to warm, wet conditions for long periods. These deeply weathered soils often extend dozens of meters below the surface, representing the accumulated effects of millions of years of chemical attack on the underlying bedrock. The minerals that survive this intense tropical weathering are those most resistant to chemical breakdown. Quartz, with its strong silicon-oxygen bonds, can persist even under the most aggressive weathering conditions. Iron and aluminum oxides, while not present in the original rock, form as secondary minerals when other compounds are broken down by chemical weathering. These resistant minerals give tropical soils their characteristic red and orange colors, reflecting the concentration of iron oxides left behind after more soluble minerals have been removed. In contrast, weathering in cold climates proceeds much more slowly, allowing even relatively unstable minerals to persist for long periods. The thin soils typical of recently glaciated regions reflect not only the young age of these landscapes, but also the slow rate at which chemical processes operate at low temperatures. Yet even in these cold environments, weathering continues throughout the year, with freeze-thaw cycles providing physical assistance to the chemical breakdown of minerals. The seasonal variations in temperature and moisture that characterize most continental climates create rhythmic changes in weathering intensity that leave their mark in the chemical composition of streams and rivers. During warm, wet periods, weathering accelerates and streams carry higher concentrations of dissolved minerals. During cold, dry periods, chemical processes slow and mineral concentrations in surface waters often decrease. Though this effect can be masked by changes in water flow that concentrate whatever dissolved substances are present. These seasonal rhythms in weathering and mineral transport create complex patterns in the chemistry of rivers that eventually reach the sea. The timing of peak mineral transport often coincides with periods of high water flow, when rapid runoff carries large volumes of water that has had limited time for chemical interaction with rocks. Conversely, during low-flow periods sustained primarily by groundwater, mineral concentrations may be higher because groundwater has typically had much longer contact time with rock formations. The specific types of minerals released by weathering depend not only on climate, but also on the geological history of the rocks being weathered. Ancient rocks that have been deeply buried and subjected to high temperatures and pressures often contain minerals that are unstable at Earth's surface conditions. When these rocks are exposed by erosion and subjected to surface weathering, they can release unusual suites of dissolved substances that reflect their complex geological history. Metamorphic rocks, formed when existing rocks are transformed by heat and pressure deep within the Earth's crust, often contain minerals that formed under conditions very different from those at the surface. When these rocks are eventually exposed and weathered, they contribute distinctive chemical signatures to the streams that drain them. The weathering of slate, schist, and gneiss releases different combinations of dissolved substances than the weathering of limestone, sandstone, or granite. Igneous rocks, formed directly from molten material, also contribute their own characteristic chemistry to the weathering process. Fresh volcanic rocks often weather much more rapidly than ancient igneous formations because they contain minerals that crystallized under high-temperature conditions and are unstable when exposed to the low-temperature, water-rich environment at Earth's surface. The weathering of basalt, rhyolite, and other volcanic rocks can contribute significant amounts of dissolved minerals to nearby streams, particularly in regions with active volcanism. The physical structure of rocks also influences how rapidly they weather and what types of dissolved substances they release. Rocks with abundant fractures and joints provide more surface area for chemical attack and allow water to penetrate deeper into the rock mass. Massive, unfractured rocks weather more slowly because chemical reactions are limited to the outer surface where water can make contact with mineral grains. The grain size of minerals within rocks affects weathering rates because smaller grains provide more surface area relative to their volume. Fine-grained rocks like shale often weather more rapidly than coarse-grained rocks like granite, even when they contain similar minerals. The arrangement of minerals within rocks also matters, as some mineral assemblages are more stable than others when exposed to surface conditions. Even the orientation of rock formations influences weathering patterns because it affects how water flows across and through the rock mass. Steeply dipping rock layers may shed water quickly, providing limited time for chemical reactions, while gently dipping formations may allow water to percolate slowly through the rock, maximizing the time available for mineral dissolution. The role of organic matter in accelerating chemical weathering extends far beyond the simple production of organic acids by plant roots and soil organisms. The complex organic molecules produced by living systems can form chemical complexes with dissolved metals that make them much more soluble than they would be in pure water. These organic complexing agents, known as ligands, can dramatically increase the rate at which certain minerals dissolve, particularly those containing iron, aluminum, and other metals. The organic matter that accumulates in soils creates chemical environments that can be far more corrosive to minerals than pure rainwater. As organic compounds decompose, they produce not only organic acids, but also a variety of other reactive substances that participate in weathering reactions. The carbon dioxide produced by decomposition dissolves in soil water to create carbonic acid concentrations much higher than those found in atmospheric precipitation. Different types of organic matter produce different effects on weathering rates and mineral dissolution patterns. The organic acids produced by coniferous forests differ from those produced by deciduous forests, leading to different weathering signatures in streams draining these different ecosystems. Grasslands produce their own distinctive suite of organic compounds that affect mineral dissolution in ways that differ from forested areas. The seasonal cycles of organic matter production and decomposition create temporal variations in weathering intensity that can be detected in the chemistry of streams and rivers. During periods of rapid plant growth, the production of organic acids increases, accelerating the dissolution of minerals in the surrounding soil. During dormant periods, when biological activity slows, the chemical attack on minerals decreases correspondingly. Even microscopic organisms play crucial roles in mineral weathering through their metabolic activities. Bacteria and fungi can produce acids strong enough to dissolve even resistant minerals, while also creating chemical environments that alter the stability of different mineral phases. Some microorganisms derive energy directly from chemical reactions involving rock minerals, creating biological mining operations that operate on microscopic scales, but collectively process enormous quantities of material. The biofilms that coat rock surfaces in many environments represent complex communities of microorganisms that can dramatically alter local chemical conditions. These thin layers of biological material can concentrate corrosive substances at the rock surface, while also providing protected environments where chemical reactions can proceed differently than they would in bulk solution. The symbiotic relationships between plant roots and soil microorganisms create particularly aggressive chemical environments for mineral weathering. Mycorrhizal fungi, which form partnerships with most plant species, can extend the chemical reach of root systems far beyond the physical extent of the roots themselves. These fungal networks can access and weather mineral grains that would be inaccessible to plant roots alone. The chemical communication between different organisms in soil systems also influences weathering processes in subtle but important ways. Plants can release chemical signals that attract beneficial microorganisms or that inhibit competitors, creating localized changes in soil chemistry that affect mineral dissolution rates. These biological interactions add layers of complexity to weathering processes that purely physical or chemical models cannot capture. The deep time perspective on weathering and mineral transport reveals patterns that operate on scales far beyond human experience, yet profoundly influence the world we inhabit. The rocks we see exposed at Earth's surface today represent only the most recent chapter in a story that extends back billions of years. Each rock formation carries within it the chemical signature of its formation and subsequent weathering history. Ancient weathering surfaces, preserved in the geological record, provide evidence of how climate and atmospheric composition have changed over Earth's history. Paleosols, ancient soil horizons now preserved as rock layers, show that weathering processes have operated throughout geological time, though sometimes under conditions very different from those that exist today. During the early history of Earth, when atmospheric oxygen levels were much lower than today, weathering proceeded according to different chemical rules. Iron, which today oxidizes rapidly in the presence of atmospheric oxygen, remained in reduced forms that behaved very differently during weathering and transport. The red iron oxide minerals that characterize many modern soils were rare or absent during much of Earth's early history. The evolution of land plants fundamentally altered weathering processes by creating the first true soils, and by dramatically changing the chemical environment at the land's surface. Before plants colonized the land, weathering was limited to purely physical and chemical processes operating on bare rock surfaces. The evolution of root systems and organic matter production created new pathways for chemical attack on minerals and established feedback loops between biological activity and mineral weathering. Even the position of continents has influenced global weathering patterns over geological time. As the continents have drifted across Earth's surface, they have passed through different climate zones that dramatically affected weathering rates and the types of minerals being transported to the oceans. The collision of continents to form mountain ranges has periodically exposed fresh rock to weathering while also altering regional and global climate patterns. The breakup of supercontinents has created new ocean basins and changed the patterns of atmospheric and oceanic circulation that govern regional climate. These changes in turn affect weathering rates and mineral transport patterns, creating long-term variations in the chemical input to the oceans that can persist for millions of years. The ice ages that have punctuated Earth's recent geological history provide examples of how climate changes can rapidly alter weathering and mineral transport processes. During glacial periods, vast ice sheets covered much of the northern continents, dramatically reducing chemical weathering rates in these regions, while simultaneously creating new landscapes through glacial erosion. When these ice sheets retreated, they left behind landscapes of freshly ground rock that experienced very rapid weathering as they were exposed to surface conditions for the first time. The pulse of mineral-rich water that flowed from these newly deglaciated regions contributed enormous quantities of dissolved substances to the oceans, temporarily altering global ocean chemistry. The lake systems that formed in glacially carved basins provide natural laboratories for studying how weathering and mineral transport operate in isolated systems. These lakes, fed primarily by streams draining recently exposed rock, often show rapid changes in water chemistry as weathering processes establish new equilibria in the disturbed landscape. The marine organisms that remove dissolved minerals from seawater represent some of the most sophisticated chemical processing systems on our planet. These biological systems have evolved precise mechanisms for extracting specific ions from the complex solution that is seawater, often concentrating these substances by factors of thousands or millions compared to their concentrations in the surrounding water. The calcium carbonate shells built by marine organisms require the extraction of calcium and carbonate ions from seawater in exact stoichiometric proportions. This biological precipitation of minerals from seawater represents one of the largest chemical fluxes on our planet, removing billions of tons of dissolved substances from the oceans each year. The organisms that carry out this process range from microscopic single-celled creatures to massive coral colonies, but they all share the ability to control crystal formation with remarkable precision. The process by which organisms build shells and skeletons involves much more than simple precipitation of minerals from solution. Living systems can control the size, shape, and internal structure of crystals in ways that purely chemical processes cannot achieve. The result is biological minerals that often have properties superior to their geological counterparts, demonstrating that life has found ways to improve upon purely physical and chemical processes. The timing of shell and skeleton formation in marine organisms often follows biological rhythms that create seasonal variations in the rate of mineral removal from seawater. During periods of high biological productivity, when many organisms are actively growing and reproducing, the extraction of dissolved minerals from seawater increases dramatically. During less productive periods, this biological mining slows, allowing dissolved substances to accumulate in the water. The evolution of shell-building organisms throughout Earth's history has fundamentally altered ocean chemistry by creating new pathways for removing dissolved substances from seawater. The first organisms to build calcium carbonate shells appeared in the geological record about 540 million years ago, marking the beginning of a major change in how the ocean system processes dissolved minerals. The diversity of shell-building organisms has increased dramatically over geological time, with different groups evolving different strategies for extracting and utilizing dissolved minerals. Some organisms build shells from calcium carbonate, others from silica, and still others from organic compounds reinforced with mineral particles. Each of these biological strategies represents a different pathway for removing dissolved substances from seawater. The seasonal and annual cycles that govern the growth of shell-building organisms create rhythmic patterns in the rate of mineral removal from seawater that can be detected in the chemistry of both the water and the resulting shell material. These biological rhythms, recorded in the growth bands of shells and corals, provide detailed records of past environmental conditions and help scientists understand how biological processes have influenced ocean chemistry over time. The death and decomposition of marine organisms represents the other half of the biological cycle that processes dissolved minerals in seawater. When shell-building organisms die, their mineral structures begin a journey that may last millions of years before they are permanently removed from the ocean system. Some shells dissolve back into seawater soon after death, returning their mineral content to solution. Others settle to the seafloor and become incorporated into sedimentary deposits. The fate of these biological minerals depends on the chemical conditions they encounter as they sink through the water column and settle on the seafloor. In some parts of the ocean, the deep water is corrosive enough to dissolve calcium carbonate shells before they can be buried in sediments. In other areas, shells can accumulate into thick deposits that eventually become limestone formations. The deep ocean circulation patterns that distribute dissolved substances throughout the world's ocean basins operate on timescales that dwarf most biological processes, yet profoundly influence the chemical environment that marine organisms experience. These circulation patterns, driven by differences in temperature and salinity, create a global conveyor belt that moves water masses around the planet over periods of hundreds to thousands of years. As water masses travel through this global circulation system, they undergo chemical changes that reflect their interactions with marine life, sediments, and the atmosphere. Water that sinks in polar regions carries with it the chemical signature of surface conditions, including high concentrations of dissolved oxygen and nutrients. As this water travels through the deep ocean, it gradually loses oxygen while gaining dissolved substances released by decomposing organic matter. The upwelling of deep water to the surface in certain regions brings these chemically modified water masses back into contact with the atmosphere and with surface-dwelling organisms. This upwelling represents a crucial link in the global ocean circulation system, returning nutrients to surface waters while also bringing deep water chemistry to the surface where it can affect biological processes. The timescales of this deep ocean circulation are so long that water sinking in the North Atlantic today may not return to the surface until it reaches the Pacific Ocean hundreds of years from now. During this long journey through the deep ocean, the water will undergo continuous chemical modifications that reflect its interactions with the sediments, organisms, and chemical processes it encounters along the way. The chemical gradients that develop in the ocean as a result of this circulation create environments where different types of chemical reactions can proceed. The oxygen-rich surface waters support different chemical processes than the oxygen-poor deep waters, leading to depth-dependent variations in the rates of various chemical reactions that affect the overall chemistry of seawater. The interaction between ocean circulation and marine biology creates complex feedback loops that help regulate both the chemical composition of seawater and the productivity of marine ecosystems. Changes in circulation patterns can alter the distribution of nutrients and dissolved oxygen, affecting where and when marine organisms can thrive. Changes in biological activity can alter the chemistry of seawater in ways that affect circulation patterns. These feedback loops operate on timescales ranging from seasonal cycles to geological ages, creating a dynamic system that maintains approximate chemical balance while continuously adjusting to changing conditions. The stability of ocean chemistry over geological time reflects not static conditions, but rather the operation of these feedback mechanisms that resist large changes in seawater composition. The role of seafloor sediments in processing dissolved substances from seawater extends far beyond simple burial and preservation. The sediments that accumulate on the ocean floor create chemical environments where a wide variety of reactions can proceed, some removing dissolved substances from seawater and others returning previously buried materials to solution. The boundary between seawater and seafloor sediments represents one of the most chemically active interfaces on our planet. Here, the organic matter that settles from the overlying water column begins to decompose, creating chemical conditions that can dramatically alter the composition of both the sediments and the overlying water. This decomposition process consumes dissolved oxygen from seawater while releasing carbon dioxide, nutrients, and other dissolved substances. The depth of oxygen penetration into seafloor sediments varies dramatically depending on the rate of organic matter accumulation and the chemical composition of the sediments themselves. In areas where large amounts of organic matter settle to the seafloor, oxygen is consumed rapidly and may penetrate only a few centimeters into the sediments. In areas with low organic matter input, oxygen may penetrate several meters into the seafloor. Below the zone of oxygen penetration, different chemical processes take over that can have very different effects on the chemistry of dissolved substances in the sediments and overlying water. In the absence of oxygen, bacteria use other dissolved substances as oxidants, leading to the reduction of sulfate, nitrate, and eventually organic matter itself. These anaerobic processes can dramatically alter the chemistry of sediment pore waters and create conditions where previously stable minerals dissolve, while new minerals precipitate. The chemical gradients that develop within seafloor sediments create environments where dissolved substances can be concentrated or depleted relative to their concentrations in overlying seawater. Iron and manganese, for example, can be mobilized in the oxygen-free zone of sediments and then reprecipitated at the sediment-water interface, creating concentrated deposits of these metals. The cycling of dissolved substances between seawater and seafloor sediments operates on timescales ranging from days to millions of years, depending on the specific chemical processes involved and the rate of sediment accumulation. Some reactions occur rapidly as organic matter decomposes, while others proceed slowly as minerals equilibrate with changing chemical conditions over geological time. The compaction and burial of sediments gradually removes them from active chemical exchange with overlying seawater. But this process can take millions of years in areas where sedimentation rates are slow. During this long burial process, chemical reactions continue within the sediments, gradually altering their composition and sometimes creating entirely new mineral phases. The interaction between tectonics and ocean chemistry creates another dimension of complexity in the processes that govern seawater composition. As tectonic plates move and interact, they create new oceanic crust while destroying old crust, continuously recycling the materials that make up the ocean floor. This geological recycling affects ocean chemistry by exposing fresh volcanic rock to chemical weathering, while also removing old sediments from the ocean system. The subduction of oceanic crust at convergent plate boundaries carries sediments and altered oceanic rocks deep into the Earth's interior, where they may eventually be melted and recycled through volcanic processes. This deep recycling of oceanic materials operates on timescales of hundreds of millions of years. Yet it represents an important pathway for removing dissolved substances from the ocean system over geological time. The creation of new oceanic crust at mid-ocean ridges provides fresh volcanic rock that can interact chemically with seawater, adding some dissolved substances while removing others. The heat generated by this volcanic activity drives the hydrothermal circulation systems that we explored earlier, creating chemical exchange between seawater and hot rock that profoundly influences ocean chemistry. The movement of continents over Earth's surface affects ocean chemistry by changing the patterns of river input and the geographic distribution of different types of weathering environments. As continents drift into different climate zones, the rate and character of chemical weathering changes, altering the flux of dissolved substances from land to sea. The collision of continents creates mountain ranges that expose fresh rock to weathering, while also affecting regional climate patterns. The chemical weathering of these newly exposed rocks can contribute pulses of dissolved substances to the ocean system, temporarily altering the chemical balance that maintains stable seawater composition. The opening and closing of ocean basins through continental drift affects the circulation patterns that distribute dissolved substances throughout the ocean system. New ocean basins create new pathways for water circulation, while the closure of existing basins can isolate water masses and allow them to develop distinctive chemical signatures. These tectonic influences on ocean chemistry operate on timescales of millions to hundreds of millions of years, yet their cumulative effects have shaped the chemical evolution of seawater throughout Earth's history. The chemical composition of ancient seawater, preserved in the mineral deposits and fossils found in marine sedimentary rocks, provides evidence of how these long-term tectonic processes have influenced ocean chemistry over geological time. The volcanic processes that occur both on land and beneath the sea contribute their own distinctive chemistry to the global circulation of dissolved substances. Volcanic eruptions release gases and dissolved minerals directly into the atmosphere and water systems. These contributions, while relatively small compared to the massive circulation systems we've been exploring, add their own distinctive chemical signatures to the global mix of dissolved substances. When volcanoes erupt, they release not only molten rock and ash, but also vast quantities of gases that dissolve readily in water. Sulfur dioxide, hydrogen sulfide, and other volcanic gases react with atmospheric moisture to create acids that make rainfall more corrosive to rocks over vast regions downwind of major eruptions. These volcanic contributions to atmospheric chemistry can persist for months or years after major eruptions, subtly altering weathering rates across entire continents. The ash and volcanic debris scattered by eruptions provide fresh mineral surfaces that weather much more rapidly than older, more stable rock formations. Volcanic ash with its enormous surface area and chemically reactive composition, can contribute significant amounts of dissolved minerals to streams and rivers in the years following major eruptions. This pulse of enhanced weathering gradually diminishes as the volcanic materials are buried or incorporated into more stable soil systems. Underwater volcanic activity contributes directly to ocean chemistry through both explosive eruptions and the more gradual extrusion of lava flows onto the seafloor. When molten rock contacts seawater, it creates conditions of extreme temperature and pressure that drive rapid chemical reactions between the rock and water. These reactions can alter the chemistry of large volumes of seawater in the immediate vicinity of underwater volcanic activity. The volcanic islands that dot the world's oceans provide natural laboratories for studying how fresh volcanic rocks interact with seawater and atmospheric precipitation. These islands, built entirely from volcanic materials erupted from the seafloor, experience some of the most rapid weathering and erosion rates found anywhere on Earth. The streams flowing from these volcanic islands often carry concentrations of dissolved minerals that are much higher than those found in rivers draining older continental rocks. The geothermal features associated with volcanic activity create their own unique contributions to the global circulation of dissolved substances. Hot springs, geysers, and fumaroles bring deep groundwater to the surface, carrying dissolved minerals that have been extracted from hot rocks far beneath the surface. These thermal features often produce water with mineral concentrations approaching those of seawater itself, though from entirely different geological sources. Even in areas without obvious volcanic activity, the slow cooling of igneous rocks deep beneath the surface creates ongoing chemical exchange between groundwater and hot rock. This deep circulation of groundwater through cooling magma chambers contributes a steady stream of dissolved minerals to surface water systems, though at rates much slower than those associated with active hydrothermal systems. The role of time in these geological processes cannot be overstated. The cycles we've been exploring operate on scales that challenge human comprehension, unfolding over millions and billions of years with a patience that dwarfs all human experience. Yet it is precisely this vast temporal scale that allows such apparently slow processes to create such profound effects. Consider that every grain of salt in the ocean began its journey as part of a crystal in some ancient rock formation. Each sodium ion was once locked in the crystal structure of feldspar or some other silicate mineral, held in place by chemical bonds that seemed permanent and unbreakable. Yet given enough time and the gentle but persistent action of slightly acidic water, even these strong chemical bonds eventually yielded, releasing their constituent atoms to begin the long journey toward the sea. The limestone that forms the backbone of many mountain ranges began as countless microscopic shells drifting in ancient seas. Each tiny shell represented the lifework of a marine organism that extracted dissolved calcium and carbonate from seawater and transformed these simple ions into complex crystalline structures. When these organisms died, their shells settled to the seafloor, gradually accumulating into deposits that would eventually become solid rock through the slow process of burial and compression. The mountains themselves, seemingly permanent fixtures of the landscape, represent temporary accumulations of rock that will eventually be worn down and carried to the sea grain by grain. The highest peaks that tower above us today are already being attacked by frost, wind, and the patient chemical action of rainwater. Given enough time, even the mightiest mountains will be reduced to dissolved ions flowing in rivers toward distant oceans. This perspective of deep time reveals that the distinction between fresh and salt water that seems so fundamental to our experience is actually part of a continuous process of transformation. The fresh water that falls as rain today carries within it the potential to become part of the salty sea, just as the salt water of the ocean carries within it the potential to rise as fresh vapor into the atmosphere. These transformations occur according to physical and chemical laws that operate with perfect consistency across all scales of space and time. The water molecule that you might drink today in a glass of fresh water could have spent the last 1,000 years as part of a deep groundwater system, slowly dissolving minerals from ancient rock formations. Before that, it might have been part of an ice sheet at the polar caps, and before that, it might have risen as vapor from a tropical ocean on the other side of the planet. Each phase of this journey involved the same fundamental processes we've been exploring, the same selective behavior of evaporation, the same patient work of chemical weathering. The salt ions dissolved in seawater carry their own ancient histories. A sodium ion drifting in the Pacific Ocean might have been weathered from granite in the Himalayas, carried by the Ganges river system to the Indian Ocean, and then transported by ocean currents across vast distances over periods of centuries or millennia. The chloride ion that it will eventually bond with to form salt might have originated from the weathering of completely different rocks on a different continent, carried to the sea by entirely different river systems. These individual ionic journeys, multiplied across countless trillions of dissolved particles, create the complex chemistry that characterizes modern seawater. Yet despite this complexity, the overall composition of seawater remains remarkably constant across all the world's oceans. This uniformity reflects the thorough mixing accomplished by ocean currents over the geological timescales required for these chemical cycles to operate. The stability of seawater composition over such vast timescales suggests that Earth's ocean atmosphere system contains powerful self-regulating mechanisms that resist large changes in fundamental chemical parameters. When inputs of dissolved substances increase, removal processes tend to accelerate. When inputs decrease, removal processes slow correspondingly. This dynamic balance has maintained ocean conditions suitable for life over billions of years of Earth history. Understanding these self-regulating mechanisms helps explain how our planet has remained habitable, despite enormous changes in solar brightness, atmospheric composition, and continental configuration over geological time. The chemical cycles that separate fresh from salt water are part of a larger system of planetary regulation that has maintained surface conditions within the narrow range required for liquid water and, ultimately, for life itself. The emergence of life on our planet represents both a consequence of these chemical cycles and a profound modification of them. Living systems depend absolutely on the availability of fresh water for their basic metabolic processes, yet they have also evolved to participate actively in the global circulation of dissolved substances. Plants extract minerals from soil and concentrate them in their tissues. Animals transport minerals across landscapes through their movements and waste products. Marine organisms extract dissolved substances from seawater and incorporate them into biological structures. These biological modifications of the global chemical cycles have become so extensive that they now represent major components of the planetary system that regulates seawater composition. The limestone formations that store vast quantities of carbon extracted from ancient atmospheres consist almost entirely of biological minerals precipitated by marine organisms. The oxygen in our atmosphere, which affects the chemistry of weathering reactions, is almost entirely a product of photosynthesis by plants and marine algae. The evolution of human civilization represents the most recent chapter in this long story of biological modification of planetary chemistry. Human activities now influence the global circulation of dissolved substances through agriculture, mining, industrial processes, and the burning of fossil fuels. These activities operate on timescales much faster than the geological processes we've been exploring, potentially creating rapid changes in chemical cycles that have remained stable for millions of years. Yet even human modifications of these ancient cycles must ultimately conform to the same physical and chemical laws that have governed planetary processes since Earth formed. Water will continue to evaporate selectively, leaving dissolved substances behind. Rocks will continue to weather at rates determined by temperature, acidity, and mineral composition. Rivers will continue to carry dissolved minerals toward the sea, where biological and geological processes will continue to work toward chemical balance. The resilience of these natural cycles, their ability to continue functioning even under changing conditions, reflects the deep stability of the physical laws that govern matter and energy throughout the universe. The quantum mechanical principles that determine how electrons are shared in chemical bonds also control the large-scale processes that shape planetary surfaces. The thermodynamic laws that govern the evaporation of individual water molecules also drive the circulation patterns that distribute heat and moisture around entire planets. In contemplating these connections between the smallest and largest scales of natural processes, we begin to appreciate the profound unity that underlies the apparent complexity of Earth's systems. The saltiness of the sea and the freshness of rain emerge from the same fundamental physics that governs the behavior of atoms and molecules everywhere in the universe. These processes operate according to mathematical principles so elegant and universal that they seem to express something essential about the nature of reality itself. As we draw near the end of our gentle exploration through the vast cycles that govern our planet's waters, let yourself rest in the knowledge that these ancient processes continue their patient work with a reliability that has sustained life for billions of years. The same forces that created the oceans and shaped the continents continue to operate today with undiminished power, maintaining the delicate chemical balance that makes our living world possible. The rain that falls tonight carries within it the memory of ancient seas, though it arrives at your doorstep as pure and fresh as if it had never known salt. The ocean waves that crash on distant shores carry dissolved minerals that began their journey in rocks older than complex life itself, yet they participate in the same ongoing cycles that will continue long after our own brief moment in Earth's history has passed. In the quiet operation of these planetary cycles, we find something deeply comforting about the natural order that surrounds us. These processes ask nothing of human consciousness or intervention, yet they provide the foundation for everything we experience. They operate with a patience and precision that dwarfs all human effort, yet they create conditions that allow consciousness itself to emerge and contemplate its own origins. The water cycle that creates fresh rain from salty seas represents one of nature's most elegant solutions to the challenge of maintaining chemical balance on a planetary scale. It operates through the simple physics of molecular behavior, yet it creates conditions complex enough to support the incredible diversity of life we observe around us. In its quiet efficiency, we glimpse something of the deeper patterns that govern all natural systems. Tonight, as you prepare for sleep, remember that you are made largely of water that has participated in these ancient cycles countless times. The hydrogen and oxygen atoms that compose the water in your body carry within them the history of their journey through clouds and rivers, through the bodies of other living creatures, through the deep circulation systems of the oceans themselves. You are quite literally composed of materials that have traveled the world many times over, participating in the same cycles that separate salt from fresh water. As your breathing slows and your consciousness begins to drift towards sleep, let yourself feel connected to these vast cycles that operate beyond the reach of human awareness, yet sustain everything we know and love. The distinction between fresh and salt water that has guided our exploration tonight is just one manifestation of processes so fundamental that they seem woven into the fabric of existence itself. In the morning, the sun will rise again to power another day of evaporation, another cycle of the great circulation that maintains chemical balance across our planet. Fresh water will rise from salty seas, clouds will form in the endless sky, and rain will fall to nourish the land before beginning its slow journey back to the ocean. These cycles will continue with the same patient reliability they have shown for billions of years, asking nothing of us except perhaps our wonder and gratitude. The gentle separation of salt from fresh water proceeds now in the darkness, operating by physical laws so consistent and reliable that we can trust them completely. Water molecules are gaining energy from the last warmth of the day, breaking free from ocean surfaces around the world to begin their atmospheric journey as pure vapor. Somewhere else in the world, rain is falling on ancient rocks, beginning the slow chemical processes that will eventually carry new minerals to the sea. These processes connect every drop of water on Earth into one vast, interconnected system that has been operating since liquid water first appeared on our planet's surface. They represent the quiet background against which all of Earth's drama has played out, the stable foundation that has allowed life to evolve, flourish, and ultimately develop the capacity to understand its own origins. In the end, the mystery of why seas are salty but rain is not opens into something far more wonderful than we might have imagined. It reveals a planet-wide system of exquisite balance and precision, operating according to physical laws so fundamental that they connect the smallest molecular interactions to the grandest geological processes. It shows us a world where matter is neither created nor destroyed, but simply changes form, participating in cycles of transformation that have sustained our living planet for eons. As you rest now in the knowledge of these ancient cycles, let yourself feel the deep peace that comes from understanding our place in something so much larger than individual human experience. You are part of these cycles, composed of materials that have traveled through them countless times, sustained by processes that operate with perfect reliability regardless of human awareness or concern. The water that composes most of your body has fallen as rain and flowed in rivers, has risen as vapor and condensed in clouds, has been incorporated into countless other living beings throughout the long history of life on Earth. Tonight, as you sleep, these same water molecules will continue their patient circulation through your body, carrying nutrients and removing waste products according to the same physical principles that govern the global water cycle. In this quiet recognition of our deep connection to planetary processes, we find not just scientific understanding, but a source of profound comfort. We are not separate from nature, but part of it, not observers of these cycles, but participants in them. The distinction between self and environment, between human and natural, dissolves into a larger recognition of the fundamental unity that underlies all existence. The saltiness of the sea and the freshness of rain are not just facts to be understood, but invitations to wonder at the elegant mechanisms that sustain our world. They remind us that the most ordinary experiences, the taste of ocean spray and the touch of raindrops, connect us to processes that span the deepest reaches of space and time. As you drift towards sleep, carried by the rhythm of your own breathing, remember that this rhythm too participates in the global circulation of matter and energy that maintains our living planet. The oxygen you breathe was produced by photosynthesis. The carbon dioxide you exhale will be used by plants and marine algae. The water vapor in your breath will rejoin the atmospheric circulation that brings fresh rain from salty seas. In sleep, your conscious mind will rest, while your body continues its own quiet participation in the cycles that sustain all life. Your heartbeat will continue its steady rhythm, circulating water and dissolved substances through your body, according to the same physical principles that circulate water through the global system. Your cells will continue their metabolic activities, processing the same chemical elements that have been cycling through living systems for billions of years. Tomorrow, you will wake refreshed, having participated unconsciously in the same cycles of renewal and transformation that maintain our planet's chemical balance. The water you drink will be fresh and pure, separated from dissolved minerals by the same selective evaporation that operates globally. The air you breathe will be cleansed and renewed by the same atmospheric circulation that distributes moisture around the world. And in these simple, everyday experiences of drinking fresh water and breathing clean air, you will continue to participate in the ancient cycles that connect all life on Earth. The mystery of salt and fresh water that began our journey tonight will continue to operate in the background of your daily experience. A quiet reminder of the elegant mechanisms that sustain our world. Rest now in the knowledge that these cycles continue their patient work through the night, and will continue long after we are gone, maintaining the conditions that make life possible through processes so reliable and persistent that they have become the foundation for everything we experience. In their quiet operation, we find not just the answer to scientific questions, but a source of deep peace and wonder at the magnificent complexity and order that underlies our everyday world. The gentle circulation of water from sea to sky, to land and back to sea again, proceeds now in the darkness, carrying out the same patient work of separation and renewal that has sustained our planet for billions of years. In this endless circulation, salt and fresh water maintain their ancient dance, each playing its essential role in the vast symphony of processes that we call Earth. Sleep well, knowing that you rest within these cycles, sustained by them, part of them, connected through them to every living thing that has ever existed on our remarkable planet. The mystery of salt and fresh water has become a doorway into wonder, and through that doorway, we glimpse the profound order and beauty that governs the natural world. Tonight, as the last light fades from the sky and the world settles into its quiet rhythm, these ancient processes continue their patient work with the same gentle persistence they have shown for countless eons. Somewhere in the darkness, water molecules are breaking free from ocean surfaces, beginning their atmospheric journey with no memory of the dissolved minerals they leave behind. In other places, rain falls softly on exposed stone, starting chemical reactions so gradual they would be invisible to our eyes, yet so persistent they reshape entire continents given enough time. The ocean itself, vast and seemingly unchanging, pulses with currents that have been flowing for millions of years, carrying dissolved substances from one corner of the planet to another in a circulation so slow and steady it operates like a planetary heartbeat. These currents move with the patience of geological time, distributing heat and minerals and dissolved gases in patterns that have sustained marine life since the earliest days when simple organisms first learned to extract calcium from seawater to build their protective shells. Deep beneath the waves, in the perpetual darkness of the abyssal plains, sediments continue their slow accumulation on the seafloor. Each grain that settles carries with it the chemical signature of its origin, whether from the erosion of distant mountains, the remains of microscopic marine life, or the fine dust carried by winds across entire oceans. This sediment, layer upon layer, creates a geological record of Earth's chemical history that stretches back hundreds of millions of years. The chemistry recorded in these deep-sea sediments tells the story of how our planet's surface has changed over time, how the atmosphere has evolved, how life itself has modified the circulation of elements between land, sea, and sky. In the alternating layers of different sediment types, scientists can read the history of ice ages and warm periods, of times when the ocean was more or less salty than today, of periods when volcanic activity was more intense and when it was quiet. Yet through all these changes, the fundamental process that separates salt from fresh water has continued without interruption. The same physical laws that govern the evaporation of water molecules today operated when the first oceans formed billions of years ago. The same chemical principles that control the weathering of rocks today were at work when the earliest continents emerged from primordial seas. This continuity across such vast spans of time reveals something profound about the nature of our universe. The forces that shape our world operate according to mathematical relationships, so fundamental and universal that they remain constant across all scales of space and time. The attraction between electrically charged particles that keeps salt ions dissolved in seawater follows the same laws that govern the behavior of atoms in distant stars. The thermodynamic principles that drive evaporation and condensation operate with the same precision in a laboratory beaker and in the vast atmospheric systems that encircle our planet. In the gentle operation of these natural laws, we find a source of deep comfort and stability. No matter how much the surface details of our world may change, the underlying principles that govern matter and energy remain constant and reliable. The water that rises from the ocean today as pure vapor will follow the same physical laws that have governed evaporation since liquid water first appeared on Earth's surface. The rain that falls tomorrow will be fresh for the same reasons that rain was fresh when the first land plants were evolving, when the dinosaurs walked the Earth, when the earliest human ancestors were learning to use tools. The chemical processes that weather rocks and transport minerals to the sea today operated in the same way when the continents were arranged in completely different configurations, when the climate was drastically different, when life itself was just beginning to modify the planet's chemistry. This deep continuity connects us to the entire history of our planet in ways that transcend our individual existence. The elements that compose our bodies have been cycling through these planetary systems for billions of years, participating in the same chemical reactions, following the same physical laws, maintaining the same delicate balance between creation and destruction that characterizes all natural processes. The carbon atoms in your body were once dissolved in ancient seas as carbon dioxide were incorporated into the shells of marine organisms that lived millions of years ago, were buried in sedimentary rocks, and later released through weathering and volcanic activity. The calcium in your bones was extracted from seawater by some long-extinct marine creature, became part of a limestone formation, was weathered from exposed rock, carried by rivers to the sea, and eventually found its way into the food chain that nourishes terrestrial life. Even the oxygen you breathe carries within it the history of these ancient cycles. Most of the oxygen in our atmosphere was produced by photosynthesis in marine algae and land plants over billions of years. Each molecule of oxygen has likely been incorporated into countless living organisms, has participated in countless chemical reactions, has cycled between the atmosphere, the oceans, and the rocks of the Earth's crust in patterns that connect all life into one vast, interconnected system. The water that composes most of your body has almost certainly travelled through these global cycles many times, spending periods as vapour in the atmosphere, as liquid in rivers and oceans, as ice in glaciers and snowfields, as groundwater slowly percolating through rock formations over thousands of years. Each phase of this journey involved the same fundamental processes we've been exploring, the same selective separation of pure water from dissolved substances, the same patient chemical reactions between water and rock. Tonight, as you rest, your body continues its own participation in these ancient cycles. Your kidneys work to maintain the precise chemical balance of your blood, extracting excess salts and other dissolved substances while conserving the water your cells need to function. This biological process mirrors on a microscopic scale the same separation of salt and fresh water that operates globally through evaporation and precipitation. Your cells themselves represent sophisticated chemical processing systems that rival the complexity of any geological process. They extract specific substances from the surrounding fluid, incorporate them into biological structures, and release waste products back into circulation. These cellular processes follow the same chemical principles that govern the formation of minerals in rocks, the dissolution of substances in water, the precipitation of compounds from solution. The metabolism that sustains your life operates according to the same thermodynamic laws that drive evaporation from ocean surfaces and the circulation of deep ocean currents. Energy flows through your body in patterns that mirror the flow of energy through planetary systems, always moving from areas of high concentration to low concentration, always seeking equilibrium while maintaining the complex organization that makes life possible. Even your breathing participates in the global circulation of gases that helps regulate planetary chemistry. The oxygen you consume was produced by photosynthesis. The carbon dioxide you release will be used by plants and marine algae. The water vapor you exhale will rejoin the atmospheric circulation that brings fresh rain from salty seas. In these simple biological processes, you maintain direct connection to the planetary systems that have sustained life for billions of years. As sleep approaches and your conscious mind begins to quiet, your body will continue these essential chemical processes without any need for conscious control. Your heart will maintain its steady circulation of water and dissolved substances. Your liver will continue its complex chemical processing. Your kidneys will maintain the delicate balance of salts and water that keeps your cells functioning properly. All of these biological processes operate according to the same physical and chemical laws that govern the global separation of salt and fresh water. The reliability of these natural laws provides a foundation of stability that allows consciousness itself to emerge and contemplate its own origins. The same chemical elements that participate in the vast geological cycles that shape our planet also participate in the intricate biochemical processes that create and sustain awareness. The boundary between living and non-living systems becomes less distinct when we recognize that both follow the same fundamental principles of chemistry and physics. In this recognition, we find not a reduction of the mystery of life, but an expansion of our appreciation for the profound order that underlies all existence. The emergence of consciousness from unconscious matter represents not a violation of physical law, but its most elegant expression. The same forces that separate salt from fresh water in the global ocean also organize matter into the complex patterns that make thought and feeling possible. The water cycle that creates fresh rain from salty seas operates as a vast planetary-scale system of purification and renewal that has maintained conditions suitable for life over billions of years. It represents one of nature's most elegant solutions to the challenge of maintaining chemical balance in a complex system. Through the simple physics of evaporation and condensation, it continuously separates pure water from dissolved substances while maintaining the circulation patterns that distribute both heat and materials around the planet. This system requires no conscious oversight, no external management, no periodic maintenance. It operates through the automatic consequences of physical law, maintaining itself through feedback mechanisms so subtle and reliable that they have kept our planet habitable through enormous changes in solar brightness, atmospheric composition, and continental configuration. The stability of this system over geological time provides evidence of the profound order that characterizes natural processes at all scales. Yet this stability should not be mistaken for simplicity. The water cycle involves countless interacting processes, each following its own characteristic patterns and timescales. Weather systems develop and dissipate over periods of days or weeks. Ocean currents flow over periods of months or years. Ice ages come and go over periods of thousands or millions of years. Continental drift and mountain building operate over periods of tens or hundreds of millions of years. All of these processes interact in complex ways that create the dynamic equilibrium we observe in the modern world. The chemical composition of seawater itself reflects this complex interaction of processes operating on different timescales. The major constituents of saltwater, sodium and chloride have residence times in the ocean of millions of years, meaning that these substances remain dissolved for very long periods before being removed by various geological and biological processes. Other dissolved substances have much shorter residence times, being rapidly incorporated into marine organisms or precipitated as minerals on the sea floor. This variation in residence times creates a complex chemical environment where different elements behave according to their own characteristic patterns. Some substances accumulate in the ocean over geological time. Others are maintained at steady concentrations by biological processes. Still others fluctuate in response to changes in input from rivers or removal by various mechanisms. The result is a solution far more complex than simple salt water, containing dozens of different dissolved substances in precisely controlled concentrations. The precision of this chemical control reflects the operation of feedback mechanisms that have evolved over billions of years. When the concentration of any particular substance becomes too high, processes that remove that substance from seawater tend to accelerate. When concentrations become too low, removal processes slow while input processes may increase. These feedback loops operate automatically, requiring no conscious management, yet they maintain ocean chemistry within the narrow range required for marine life. The evolution of life itself has become an integral part of these chemical regulation systems. Marine organisms extract specific substances from seawater for their biological needs, effectively mining the ocean for the materials they need to build shells, bones, and other structures. This biological mining operates on an enormous scale, removing billions of tons of dissolved substances from seawater each year and incorporating them into biological structures that may eventually become part of the geological record. When these organisms die, their remains settle to the seafloor where they begin a new phase of their chemical journey. Some biological minerals redissolve quickly, returning their constituent elements to seawater. Others are buried in sediments where they may remain for millions of years before being uplifted and exposed to weathering processes that will eventually return their elements to the active circulation system. This biological component of ocean chemistry demonstrates how life and the physical environment have become so interconnected that they function as a single, integrated system. Living organisms depend on the chemical stability of seawater for their survival, yet they also actively participate in maintaining that stability through their own biological processes. This represents one of the most remarkable features of our planet: the evolution of life forms that help create and maintain the environmental conditions they require for their continued existence. The timescales involved in these biological and geological processes dwarf human experience, yet operate with a reliability that has sustained our world for eons. The limestone formations that store vast quantities of carbon extracted from ancient atmospheres required millions of years to accumulate, yet they represent the collective activity of countless microscopic organisms, each one extracting tiny amounts of carbon dioxide from seawater during its brief lifetime. The coral reefs that demonstrate this biological mining on the grandest scale have been growing for thousands of years, each colony building upon the foundations left by previous generations. These living cities beneath the waves represent the accumulated work of billions of individual organisms, each one following its own biological imperatives, yet collectively creating structures that rival mountains in their scale and permanence. Even the individual organisms that build these reefs follow cycles that mirror the larger planetary processes we've been exploring. They extract dissolved minerals from seawater, incorporate them into solid structures, and eventually return them to the sediment system when they die. This biological cycling of materials operates on timescales of years to decades, much faster than geological processes, but following the same fundamental principles of matter conservation and energy flow. The seasonal rhythms that govern the growth and reproduction of marine organisms create periodic variations in the rate at which dissolved substances are extracted from seawater. During periods of high biological productivity, when many organisms are actively growing and building shells or skeletons, the chemical composition of seawater may fluctuate detectably. During less productive periods, chemical concentrations tend to stabilize as biological extraction slows. These biological rhythms add another layer of complexity to the already intricate processes that maintain ocean chemistry. They demonstrate that the chemical balance of seawater is not static, but represents a dynamic equilibrium where small fluctuations occur continuously around long-term average values. This dynamic stability allows the ocean system to respond to changes while maintaining overall chemical conditions suitable for life. The response of marine organisms to changes in seawater chemistry also provides feedback mechanisms that help stabilize ocean chemistry over longer time scales. When dissolved calcium concentrations increase, organisms that build calcium carbonate shells often increase their growth rates, removing excess calcium from solution. When concentrations decrease, growth rates may slow, allowing calcium levels to recover. These biological feedback mechanisms operate alongside the geological and atmospheric processes that regulate ocean chemistry, creating a multi-layered system of chemical control that has proven remarkably stable over geological time. The integration of biological, geological, and atmospheric processes into a single planetary system represents one of the most sophisticated examples of self-regulation found anywhere in nature. Understanding these regulatory mechanisms helps explain how Earth has maintained conditions suitable for life, despite enormous changes in external conditions over geological time. The Sun has grown significantly brighter since life first evolved. Atmospheric composition has changed dramatically. Continents have drifted into completely different configurations, yet the basic chemical conditions required for life have been maintained through the operation of these self-regulating systems. The water cycle that separates fresh from salt water represents a crucial component of this planetary regulatory system. By continuously purifying and redistributing water around the globe, it maintains the freshwater resources that terrestrial life requires, while also maintaining the chemical balance of the oceans. This dual function demonstrates the elegant efficiency with which natural processes solve multiple problems simultaneously. The selectivity of evaporation ensures that even if the ocean becomes temporarily more or less salty due to climate changes or other factors, the rain that falls on land will remain fresh and suitable for terrestrial life. This provides a buffer against changes in ocean chemistry, ensuring that land-based ecosystems remain viable even when marine systems experience significant changes. And so we reach the gentle end of our journey through the ancient cycles that govern our world's waters. We began tonight with a simple question about why the sea tastes of salt, while rain falls sweet and fresh. What we discovered was far more beautiful than any simple answer could contain. We found a planet-wide system of exquisite precision, operating through physical laws so fundamental they connect the smallest molecular dance to the grandest geological symphony. The selectivity of evaporation, the patient weathering of stone, the vast circulation of dissolved minerals from mountain peak to ocean floor. All these processes work together with a reliability that has sustained life for billions of years. They ask nothing of our understanding, require no conscious oversight, yet they maintain the delicate chemical balance that makes our living world possible. In these quiet mechanisms, we glimpse something profound about the nature of existence itself. The same forces that separate salt from fresh water also organize matter into the intricate patterns that create consciousness, that allow us to contemplate our own origins. We are not separate from these cycles, but woven into them, composed of water and minerals that have traveled these pathways countless times before finding temporary residence in our bodies. Tomorrow the sun will rise to power another day of this ancient circulation. Fresh water will rise from salty seas, clouds will gather in the endless sky, rain will fall to nourish the land before beginning its slow journey back to the ocean. These cycles will continue with the same patient reliability they have shown since the earliest days of our planet, maintaining the conditions that allow wonder itself to exist. Rest now in the knowledge that you are held within these vast and gentle rhythms, sustained by processes older than mountains, more reliable than the turning of seasons. The mystery of salt and fresh water has become a doorway into deeper mysteries, revealing a world where the most ordinary experiences connect us to the profound order that governs all existence.